Hey guys, okay, we're going to do a little bit with a distance time graph, and we're going to look at both average speed and average velocity. So if we have just a nice, constant, non-accelerated motion on a distance time graph, then our average speed is equal to the absolute value of the slope. Our average velocity is equal to just the slope. We don't have to worry about doing absolute value. So if we were to look at this graph up here for our blue line of motion, the average speed is equal to the absolute value of the slope. So we can find our slope by doing rise over run or change in y over change in x, right? So we're just going to use the full range of motion here. So from 0 to 5 seconds, so time 5 seconds minus 0 seconds. And at 0 seconds, we were at 10 meters. And by the time we got to 5 seconds, we were at 0 meters. So our ending position for this one is 0 meters. And our starting position was 10 meters. So we have the absolute value of negative 10 meters over 5 seconds. Well, it's going to be 2 meters per second, and we could ignore the negative because we're doing absolute value. Okay, now we're going to do the same thing for the red and find our average speed. So for the red, the average speed is the absolute value of, well, let's see, we're going to do 5 seconds again. So 5 seconds minus the start time of 0 seconds. But now at 5 seconds for the red line, it ends at, oops, it's up there. It ends at 10 meters. And it started at a distance of 0 meters. So now we have the absolute value of a positive 10 meters over 5 seconds. Well, it's still just going to be 2 meters per second because it's absolute value. So the red and the blue line have the same speed, the same average speed. It's just that one of them is heading one direction, one of them is heading the other direction. Okay, and if we're looking at just speed, well, that doesn't really matter because speed doesn't really involve direction, which is why we use absolute value. Okay, if though we wanted to solve for their average velocity, then we have to start accounting for direction, right? So let's do, I think we did blue then red, right? Yeah, blue. So we'll do the average velocity of blue, which is equal to the slope. Well, the slope for blue, we said we're going to do the time. So it went from 0 to 5 seconds. So 5 seconds minus 0 seconds. And at 0 seconds, it had a position of 10 meters. Remember, we have to make the pairs. And at 5 seconds, it had a position of 0 meters. So distance, time, distance, time. That's our pairs, right? At 0 meters, 5 seconds. At 10 meters, 0 seconds. So just pulling those points right off the graph. So this is not the absolute value. So now we have negative 10 meters over 5 seconds. Well, negative 10 meters divided by 5 seconds, negative 2 meters per second. Now it matters. That sign matters because now we're talking about velocity. So negative could mean that we're going south. It could mean that we're going west. If we designate right as positive, then it could mean that we're going left because now it's negative. So it's the opposite of whatever we designate to be the positive direction of motion. All right, now for the red line. Average velocity for the red line is equal to slope for the red line. Okay, so coming back up here, at a time of 5 seconds, the red is at a position of 10 meters. So 10 meters at 5 seconds. At 0 seconds, it has a position of 0 meters. So now we have a positive 10 meters over 5 seconds. So we have a slope for this one of a positive 2 meters per second, which means our average velocity for red is the exact opposite of the average velocity for blue. Kind of makes sense, right? Because they crisscross, make a perfect X. So they are exactly opposite to each other for velocity. Okay, let's move on from that to a little bit more complicated concept. Well, maybe it's more complicated, maybe it's not. Okay, so we have this graph. We have a blue line that starts at 20 meters and ends at 70, and it does that of a time from 0 to 4 seconds, it looks like. And then we have a red line that goes from 0 all the way up to 100 in the course of 8 seconds. Okay. Let's see, is that 3 or 4? I'm gonna have to use my ruler here because you know I'm old and blind. Tell you guys that all the time. Is that 3? Nope, that looks like 4. Okay. We'll make sure we get those points right. And lo and behold, it's a cartoon situation. Bugs Bunny and Roadrunner are arguing about who is faster. Bugs says he can beat Roadrunner, but Roadrunner argues he is faster at short dashes from danger. Bugs starts at 0, while Roadrunner starts at 20 meters. Bugs runs a 100-meter dash, while Roadrunner only does a 50-meter dash. Based on the graph, who is the fastest? Well, all right, if we're going for fastest, then that means we care about speed. We don't care about velocity, just speed. So let's see. We said that Bugs does the 100-meter dash, right? So that would make Bugs red. Okay, so Bugs is our red line and Roadrunner is our blue. Can't spell. There we go, blue. All right, so if Bugs is red, we're going to look at what the slope is and find his speed. Well, average speed is equal to the absolute value of the slope. Okay? If we look at this, in a course of 8 seconds, Bugs runs 100 meters. So 100 meters minus 0 meters, where he started from, over 8 seconds minus a starting time of 0 seconds. And we need to take the absolute value. Okay, so if we do that, we get 100 meters divided by 8. So Bugs has an average speed of 12.5 meters per second. Okay, we don't care. Positive, negative, doesn't matter because we took the absolute value, right? So his speed, his average speed is 12.5 meters per second. Roadrunner's average speed, oops, and I should put my average up there. That was bad of me. So Roadrunner's average speed depends on the slope of his line. Okay, well, he goes from 20 meters to 70 meters in a time of 4 seconds. So he ends at 70 meters. He starts at 20 meters. And he does that in a time of 4 seconds from a start time of 0. We're going to take the absolute value of that. Okay, 20, take away from 70, so you got 50 divided by 4. Wait a minute. 12.5 meters per second. All that arguing and bickering, and they wind up having the exact same speed. Okay. We probably could have noticed that visually. If this graph was super accurate and it wasn't being drawn by your shaky hand physics teacher who's getting old and blind, then these would be perfectly parallel, right? These lines, if they're perfectly parallel to each other, that means that their average speed is exactly the same, because parallel lines will have the exact same slope. Same slope, same speed. Okay. If they have the same slope, period, without that absolute value sign, they would also have the exact same velocity. Well, if they're both going in the same direction and they're both covering in the same speed, then they both have the same average velocity as well, because they're both headed the same direction. All right. One more to look at here. I've warned you guys, I like my cartoons. All right. So now we have Scooby-Doo and a ghost. And we all know Scooby-Doo runs from ghosts. But sometimes the ghosts tend to overshoot Scooby-Doo. So let's take a look at this problem. Scooby starts 100 meters ahead of the ghost. The ghost is chasing him, but unbeknownst to Scooby, this ghost is just a hologram. At what time does Scooby wind up actually chasing the ghost? Okay. Well, we talked a little bit about this before, that if lines cross on a distance time graph, that means that they are occupying the same exact space at the same exact time. So right here on this graph, let's see, maybe around 350, 375, because it's drawn by a shaky old person. So if we look at that right around there, right around 350, 375, they cross. Now the ghost was behind Scooby-Doo, right? They wind up side by side. And then all of a sudden, if we look over here at 400 seconds, Scooby-Doo is only at maybe 490 meters, and the ghost is further ahead at like 500 meters. Well, that means that starting from here forward in time, Scooby-Doo is now chasing the ghost. So we can look at any given instant in time and tell who's chasing who until this moment when they pass each other. Now they're both running the same direction. So if they're both running the same direction and one passes the other, we go from one being in the lead to the other being in the lead. Okay, just like two runners in a race. But now it's just Scooby-Doo and a ghost. All right, we're going to leave it there, and then we're going to go ahead and take a look at some other things in the next couple of days.